Hello everyone, welcome back. So, we started with the multidimensional flow and we saw that how in 2D you can basically extrapolate the x1 drop approach that we have seen earlier for 1D and how you can apply a limiter using the splitting approach. So, now we will go to the multidimensional flow 2D and 3D or we will look at a generalized approach. Okay. So, we will also look at generalized grid, that means we will have to go to unstructured grid. So, unstructured grid have the issue that the cells are not defined in a sequential manner like I plus 1, I plus 2 and so on and so forth, but they can be aligned in any direction, right. So, let us see how we can basically address computations on these kind of grids. Okay. So, yeah, this is the example of structured grid on the left and you have unstructured grid on the right. Okay. So, just to show you, so for example, here if you look at the grid here, okay. So, you have very nice distribution of the grid here and this is a kind of O grid that I am showing here. So, what is O grid? So, basically you have a nanophile here and you made an O shape which is the external boundary, and what you did is basically you filled in elements like this, okay, till the last boundary, and then you also had these elements, okay, everywhere. Okay. So, you can see that there is a pattern here. Okay. This is actually is a kind of curvilinear grid, right. So, for example, you can call it maybe I. So, this is I equal to, there will be 1 on the wall. So, this is I equal to 1, I equal to, or let me call it j. So, j equal to 1, j equal to 2, j equal to 3, j equal to 4 and all the way to j to let us say n j, okay, or n y, we call it n y. Similarly, if you look at I, so this may be I equal to 1, let me write it I. So, this is I equal to 1, I equal to 2, I equal to 3 all the way to let us say I equal to n x, right. So, there is a certain pattern here. Okay. It is not as simple as the grids that we have been seeing even in 2D, but there is a pattern here and there is a curvilinear transformation that you can use. You can define a Jacobian and you can actually convert it to a simple mesh like this, which will be j equal to 1 to j equal to n y and I equal to 1 to I equal to n x. Okay. So, this can be converted into a simple grid like this using a Jacobian by defining a Jacobian. Okay. So, this is the curvilinear transformation. It is only possible because there is certain nice arrangement of the points in the entire grid. Okay. So, these kind of grids are called the structured grid. If you look at the grid on the right hand side, okay, you cannot basically find a definite pattern here. Okay. So, the grids are aligned in all directions and let us say I am focusing on this particular grid here. This is a cell. Okay. Here also we have cells. Okay. So, as I mentioned that I will be talking about the finite volume, right. So, you can have basically cell centers defined everywhere here. Okay. There will be cell center here and every point that we have, whether it's small or big, you can have a cell center. Okay. And there are basically in every cell has got 4 edges. So, this one for example, this is cell center, this is edge 1, 2, 3 and 4. Okay. So, all the elements you can call these kind of elements are called the hex elements or the quadrilateral elements. Okay. So, in 2D it is quadrilateral, in 3D it will become hexahedral. Okay. So, this is the quad. Here you can see that okay, most of the elements that you have here is the tri elements. Okay. There are only 3 sides, you can have the cell center here and you have basically 3 edges 1, 2 and 3. Okay. So, these are called the tri elements, triangular elements, or if you go in 3D that will become tetrahedral elements. Okay. So, you have basically you have these tetrahedral elements and you can see for example, this cell is connected to 1, 2 and 3. Okay. And also you have cells here and here. Okay. So, there is you cannot define, for example, let us say you want to go to the higher order scheme and you want to go to I plus 2 and I plus 3, you cannot do that. There is no I or j connectivity here. Okay. All you have is, let us say if you define a direction or normal to to the flux, you can have a left cell here and right cell here. Let us say look at here. So, this is my edge. there may be left shell here and right shell here. Okay, that is the only information that we have in this kind of grids. Okay. So, you can define left and right shell on every single edge or interface, but you do not have the information of connectivity. The second problem that you have is how do you basically define the upwinding here. So, for example, in this if the flow is coming from left to right, still I mean in this you have to be little bit careful. It is not as trivial as a simple grid like this where the flow is coming from left to right, okay, because your elements are in this direction for example. But still you have a overall picture that if you can let us say convert to this grid, or if you find the phase normal, okay, you can basically define which direction the flow is happening, and you can accordingly apply the upwinding here, upwinding there. Okay. In this they are oriented in every single possible direction. Okay. You can see that the orientation of each cell is different, and if you go to very close to the grid, or okay, so the connectivity also is very different, right. So, working on this kind of grid, okay, require you to use finite volume, and sometimes finite element can also be implied in this kind of problems. Okay. Here you can apply the finite difference or finite volume both. Okay. So, the finite volume is general approach, it can be applied to structured, it can be applied to unstructured, any kind of grid that you want. Okay. But finite difference can be applied only to a structured grid. Okay. It can be uniform or non-uniform, it can be curvilinear, but it has to have a structured grid. Okay. So, that you can define the connectivity of I plus 1, j plus 1 and so on and so forth, right. Some more examples of grids, for example, this is a grid on a turbine blade. Okay. So, this in this case what we have is a block structured grid. Okay. So, you have several tools that you can use to create those grids, especially when the domain is complicated. You cannot basically make a grid using a normal let us say MATLAB code or something like that, because you have to ensure that the grids are orthogonal to one another, the skewness is not very high, the aspect ratio is not very high. So, usually there are several grid generators like for example, ICM-CFD is there, one of the popular grid generators from ANSYS, then you have Pointwise, okay, the Grid Pro, okay, GridGen, and there are several open source tools also available to generate grids. So, what these tools do is basically they will give you very nice orthogonal grid, they will give you flexibility to define different blocks and construct grid. So, here for example, this is a blade, this blade in a cascade, that means you have a blade on top also somewhere here and a blade at bottom also, right. So, we have taken the distance between these two blades and put a top boundary, so that you can apply the periodic bounding condition here. So, you can apply periodic here, okay, and similarly you can apply periodic here at the bottom. Okay. Now, there is a challenge to make grids on these kind of problems, because there is very high curvature here and very high curvature here. Okay. So, what is done here is that we made different blocks. So, you can see there is one block which is going in this direction, there is another block which is going in this direction, there is another block here. Okay. So, very close to the body there is a single block which is it is actually not a single block. So, we have basically the boundary layer which is very close to the body, this is aligned to the grid, aligned to the geometry that we have. This is what I was saying, that it is very important that you respect the curvature on the body that you have. So, if you want to let us say make a flow past a cylinder, okay, you cannot make a grid which is going like this and this and this very close to the body. I mean, if you make it, there will be lot of errors. Okay. So, what you should do that very close to the body, you should have grid which is basically conforming to the shape that we have. Okay. And away from that, you can apply unstructured grid. So, this is called the boundary layer grid. Okay. So, very close to the body, you have basically the boundary layer mesh or boundary layer grid. The same thing is done here, there is a boundary layer grid here, but then we also have like let us say block 1, block 2, block 3, block 4, then block 5. The block 5 for example goes from here to here, okay, and then block 6. So, then can be multiple blocks, and making this kind of grids requires significant amount of effort. Here also you will have many blocks, you can see in the trailing edge also 1, 2, 3 and so on and so forth, right. So, making block structured grid time consuming, but then it gives you more accuracy than unstructured grid. If you look at the unstructured grid on the same geometry that we have, Okay, now it is I am showing you a coarser version just to make a point of how things can be how the grids can be made. So, here also you can see that now you can see the elements are in all direction. Okay, there are some elements which are quad, there are some elements which are tri. Okay, so let me show you the zoom version here. So, you can see that there is a very nice boundary layer very close to the body. So, this is the boundary layer that you met. Okay, so this is basically conforming to the geometry that we have. Okay, maybe you have 20 layers or 30 layers of those boundary layers, but away from that, because the domain is very complicated, you can just fill in the unstructured elements. Now, there are several basically tricks or several guidelines or rules, not rules, basically guidelines on how to create a mesh. So, for example, the meshes should be as orthogonal as much as you can make. Okay, that is one thing. Secondly, you can the transition of mesh from, for example, from this cell to this cell should not be very high. If the transition is very high, okay, then again there will be loss of accuracy, and sometimes the code may blow up also. Okay, the skewness should not be very high, because the elements, for example, like this very thin and going like this, these kind of elements should be avoided. Okay, so there are some guidelines in creating meshes. Okay, and in fact, when you create a mesh, you can do some kind of mesh check to see whether this mesh is suitable for doing a CFD simulation. So, this is one of the most important thing that you need to do when you do a CFD simulation of any flow. Okay, if your grid is not correct, a solution will not be correct, no matter how good your flux scheme is, whether it is second order, third order, or any scheme, right. So, you need to basically put in effort for making grid, and if you look at for example, this particular grid, so you have basically elements. Okay, these are basically the quad elements. Okay, you will have certain times, let us say these are the tri elements, it has only 3 sides. Okay, here there are basically 4 sides. Okay, and then you have basically different orientations you can see at different places. Okay, and actually mesh can become much more complicated than this. Let us say the example that I talked in the beginning, let us say you have a slat and a flap and a wing, there are several gaps or multi element aerofoil and all those things. If you want to create a mesh, it can really become very tricky. Okay, let us say you want to simulate that entire aircraft with all the basically control surfaces deployed, right. Your flaps are deployed, slats are deployed, and you want to basically create a nice mesh there. Okay, so it takes really a good amount of effort to create meshes on those configurations. Okay, so I hope it is clear to you that what is structured grid and what is unstructured grid. So, now let us look at what kind of elements you might get. Okay, this is just an example, but you can have more elements in this. So, this is basically the quad elements, or it is the quadrilateral in 2D, these are in 2D, you can have tri elements. Okay, but you can also have, let us say elements like this, or you can have the hexa kind of thing like this. Okay, nothing stops you, and you can have any highly skewed element, not highly skewed element, but yeah, I mean you can have element which is not as nice as, let us say, rectangle. Okay, if you highly skewed, then again there will be some issues in convergence. Okay, triangle also can be of different shapes, right. This is for 2D. In 3D, basically you have basically the tetrahedron, and so you will have tetrahedron mesh, and then this is, for example, the hexahedron. Okay, and this is the triangular prism. Okay, and you have, for example, this is tetrahedron. Okay, so all kind of this is pyramid. Okay, so all kind of elements are possible. Okay, and this is just again illustrative. You can have many different kind of complicated elements as you go in 3D, right. So, these are different kind of elements that you might encounter. So, in every the first thing that you need to worry about is that when you do the calculations, if you recall the finite volume formulation that we have talked about, we need area and the volume. Okay, for example, if you have this kind of different elements, you need to find out that how to create the volume of every single cell, and then also you have to find out the area of the face, every single face. In the 2D, you will have area which is equivalent to the volume in 3D, and we have basically this distance which will be the area equivalent to the area in 3D, right. So, these geometric calculations are normally done in the beginning itself. Okay. So, as soon as you have the mesh, what the solver do is that it will create all these information, that what is the centroid of the face, okay, what is the cell centroid, what is the area normal direction, okay, what is the area everywhere, okay, what is the cell volume, and everything is calculated, because this information is required in every single iteration. So, you do not want to calculate it every time. Okay. So, this is the kind of preprocessor before you start the iteration. Okay. So, this is purely depending on the geometry, depending on the mesh that we have. Okay. So, now let us look at the multidimensional equations. Okay. And since we are talking about the compressor flow, so we will look at the compressor flow, and first we will start with the Euler, but then we will also go to the Navier-Stokes, because that presents some additional complications. So, this will be, this is the 3D Euler equation. If you want to do it in 1D, then these things will go to 0, okay. And if it is in 2D, then this will go to 0. Then how are what are these terms? Basically f, g, h, okay. So, I have discussed this in I think the week 4, okay. So, this is a full 3D equations, 3D Euler equations, okay. So, this is mass equation, there are 3 momentum equation, and then energy equation, and corresponding fluxes you have, okay, the flux f, flux g, and flux h. So, basically in 3 different directions you have, okay. If you want to, I mean, we have been doing it for 1D. So, if you are doing in 1D, then these things will go away, okay. Again these things will completely go away if you are doing in 1D, and this will also go away, and energy we have discussed that it is a summation of internal energy and the kinetic energy, right. So, basically we now we have to solve it. Now, how do you solve these complicated equations in a in an unstructured grid? So, just to quickly revise. So, what we had done in the 1D finite volume is that we defined this cell, okay, and then we had this cell center, okay, which is I, and then you have I plus 1 and I minus 1, and we had this interfaces or the edges, okay, and then we had this volume of the cell, and then we had basically used this Gauss divergence theorem, and finally, we had gotten this formula in terms of the fluxes in and fluxes going out. So, if you want to talk about this particular cell, okay, which is I minus half to I plus half, okay, there is cell I here, okay. So, whatever fluxes going out and getting in, the difference of that will be subtracted from the previous value, and that will give you the new update, right. So, this is what we had here, and omega I we said it is used for the cell volume. In 1D case, it is just the distance that we have from here, okay. If it is structured uniform mesh, then it is just delta x, right. So, this can be written in the integral form. So, this is del u by del t, and this is nothing but del dot f, right. So, del dot f, and then we are integrating across a cell volume. Let us say you are talking about a 3D volume like this, okay. So, every single volume that you have will you will have to basically integrate it. So, that is the finite volume, okay. Now, we will use a Gauss divergence theorem, okay. This is a very popular theorem in math, and if you have taken any engineering mathematics course, you would be knowing this is a part of the vector calculus. So, what it says is basically whatever fluxes you have at the boundary. So, let us say I have an element like this, and you have fluxes at the boundary, everywhere you have fluxes at the boundary, and I am showing this arrow, basically they are showing the face normals, they are normally outward, okay. So, these are the face normals, okay. So, whatever normal fluxes that you have everywhere, if you integrate it, okay, it will basically tell you it is equal to the summations of all the sources and sinks inside the volume. So, the divergence of f, the del dot f integrated in the volume. So, there is del dot f here. If del dot f is positive, okay, greater than 0, then it is a source, okay. In fluid dynamical sense, if there is a divergence of u which is greater than 0, okay, that means there is an expansion. If del dot u is less than 0, then it is basically compression, right. So, that is why in compressor flow these terms are not 0, in incompressible flow, that del dot u is equal to 0, right. What this Gauss divergence theorem says is that the summation of all the sources and sinks in a volume, okay, which is represented by this divergence term here, okay, is equal to whatever fluxes that you have across all the phases in that particular volume, okay, multiplied by the area that you have, right. So, this you can replace this term with this, and you will have finally this expression for general Navier-Stokes equations or Euler equation right now. Okay, so, once you do that, now this is still in the continuous form. Okay. When we talked about making a grid, what we had is basically you had number of cells, for example, let us say 1 million, okay, 10 to the power 6 or so. So, we will have basically you have a discrete number. Okay. So, we have to, and every cell has a face, has faces, okay, 1, 2, 3, 4, 5, okay, and then you have n number of cells, right. So, you need to basically convert this into discrete information. Okay. So, this is very easy, that we have discussed earlier, that you will have a cell average quantity. So, once you define this cell average quantity, which is over omega, okay, which is the cell volume, then you can replace this u with u bar, okay, and here I have not used bar, but this is the bar, okay, and this entire thing will become del u bar by del t into omega I, where u I bar is basically your cell average quantity. Okay. How do you take care of this? Okay. So, we are talking about that there is a value of flux here, okay, multiply with the normal, and then it is integrated over the area that you have. Okay. So, you may have this phase, this phase, this phase, and this phase. Okay. Whatever you have to take this f dot n, and f dot n is the normal flux, and it has to multiply in this area. So, if you want to do it in a discrete sense, so we will say that there is a linear variation of the flux, just like we have the linear variation of the value within the cell, right. So, you have this basically f dot n, right. So, you have, let us say this is your perpendicular flux, okay, and in this phase, for example, let us say the value is varying like this, okay, whatever value that you have, just like in the cell, if this is a cell, you will have variation in the cell. Similarly, you can have variation in the phase also. Okay. So, you let us say you have variation with the cell like this, and this is my area. Okay. Let us say this is A1 and A2, this is A1 to A2, correct. So, we want to make it discrete. So, what we will do is that, because just like we talked about the phase cell average quantity, we can have a value at the center of the phase. Okay. And if you are assuming a linear variation from the end to end of the phase, basically from node 1, let me call it vertex 1 and vertex 2, so V1 to V2. Okay. So, then you can define a phase center value, which is given as the value at this phase center here, okay, and whatever value that you have at the phase center, multiply by the normal, that is f dot n, okay, and this phase, and then you multiply with the area that you have. Okay. So, that area will be just given by like this. Okay. So, instead of basically talking about the variation across the phase or across the interface, what we will do is that we will take the value at the center of the phase, okay, and multiply with whatever area that we have here, okay, and we will do it for all of these, and then we will add. Okay. So, that is what I have done here. Okay. So, I have converted this continuous integration across all the phases to basically to all the number of phases that we have. In the tri it will be 3, in the quad it will be 4, if it is hexagonal that will be 6, right, with the discrete variation. So, you have f dot n at f, which is the value at the cell center, okay, and multiply by the area that you have here. Okay. So, this is a representation, a nice representation of two cells, which we call it I and j, and there is a normal which is calculated here, okay, which is going outward, and all these normals and everything has to be calculated in the beginning itself. And the calculation of normal is very important, because if you do not calculate it properly, then you will have basically issues in running the code. Okay. And you have to follow a certain direction. Okay. So, for example, your let us say my vertices are V1, V2 and V3. So, if your value you have made a cell which has counted as V1, V2, V3, then it goes from V to V3, V2 to V3 and normally in outward direction. If it is going from V3 to V2, then normal will be in this direction, right. So, you have to follow one direction, okay. You cannot keep on changing. So, many times when you create a mesh, what happens is that let us say you create the boundary mesh in one direction and the bottom in a different direction. So, sometimes you will have these issues coming up. So, that you need to take care. So, once you have all these things, so we have now the discrete update formula available with us. Okay. So, what all you need to do is this, calculate this f dot n, we call it as f perpendicular or f normal, okay, because this is a normal flux. And how do you calculate this normal flux? Basically, you will be having the values coming from the left, we call it as UL, okay, values coming from the right. Same as what we have been doing for 1D also. So, 1D we had a cell, okay, and this is the value that we have, okay. Let me make it like this. So, this was like I minus 1 and I plus 1, right. So, from this we got the value at normal here, from this we got another value here and we solve the Riemann problem here. Same thing we are doing here also. If you are doing a linear also with the limiter, we will have variations like this, okay. This value and this value, use both of these to solve the Riemann problem. So, once you have the information of the left and right cell, okay, this is also one of the tricky thing that you have to understand, because we also have to respect upwinding, okay, especially in the compressible flows. That is a very important property that we have to respect, otherwise the codes will not be stable. So, we have to have basically a definition of what is my left and what is my right, okay, because that is what will tell you the flow is happening in which direction. Okay. For example, in this particular case, this is L and this is R, only if the flow is happening in right direction. Let us say the flow is happening in right to left, then this is my left and this is my right, correct. So, we have to basically be very careful. In fact, in the earlier example, we will have left here, right here, because you will be calculating ui minus 1 by delta x, okay, when the c is greater than 0. When the c is less than 0, okay, then we will have basically ui plus 1 minus ui by delta x, okay. So, this will become left and right, okay. So, you basically need to have this phase normal defined very well, so that you can tell which one is left and which one is right. So, once you know the value of left and right and you know the value of phase normal, you can calculate the perpendicular, you sum it up across all the phases, divide by the cell volume and then use any favorite scheme, let us say Euler scheme or Runge-Kutta scheme or any scheme to basically update it. So, this is how a typical code works. Now, just one thing that I want to discuss before I close for today, that so you are working here. So, just like we had this linear variation, right. So, you will have variation across the cell also, right. If you do not use, let us say you use the constant value of the cell, okay, then if you have you will get only first order accuracy, and that too the accuracy will decrease because you are using unstructured grid, right. So, you will have to have a linear variation in the cell also, right. So, that process is called reconstruction, just like we discussed the slope limiters, right. So, we will limit the slope and we will see. So, in the 1D it was very easy, right, or even 2D if it is structured, then it is very easy to calculate a gradient, right. It is just like the value on the right and the left, okay, the difference between the two to calculate the gradient. So, gradient calculation is not very difficult for the linear reconstruction. In the cell, how do you calculate the gradient, right? So, let us say you have a cell like this or you have a cell like this, how do we calculate the gradient, and especially when you do not have your neighboring element can be like this or can be like this, okay, like this, like this, like this, okay. So, calculating gradient is not an easy task, that is one part, but secondly this information you need to calculate the gradient at I to get the value at phase, right. So, for example, if you want to calculate the value of UL here and UR here, so UL will be basically UI what is the value that you have at I, plus whatever you have the gradient del u by del x at I, okay, into delta x, plus whatever value del u by del y into I into delta y, and so on and so forth. Okay. If it is 2D, then you can write it I j maybe. I mean, you actually this does not matter, it's a finite volume, so you can't have I and j. Okay. So, and this delta x delta is like how much far you have here from the cell center. So, that will determine from the f and I, right. So, you require the gradient at this I, okay, these cells that we have, cell centers that we have, okay, at I, at j, and every single point here. But when you go to the Navier-Stokes, that is not sufficient, because you would also need the gradient to be calculated at the phase. And why is that? Is because the viscous term that you have. So, if you go to the Navier-Stokes equation, so you not only have this Euler fluxes or the inviscid fluxes, okay, you also have this viscous fluxes, okay, which is given by the FB, GB, and HB, and in the full 3-dimensional sense, it can be written in this way in the compressible flow. So, I have briefly discussed this earlier. So, you will have the viscous terms also acting on that, right. So, you will have this is tau xx, tau xy, tau xz, and tau y. So, you will have a matrix of basically all this tau xx, tau xy, tau xz, then tau yx, tau yy, tau yz. So, they are in 3D, for example, tau zx, tau zy, and tau zz, okay, and there are basically 6 independent elements, okay, and all these stresses need to be calculated. Then you will have this term coming due to the thermal conductivity, okay, because of the energy equation you have, right. So, basically Q is basically minus K del T by del x, for example, Qx, right. So, K is the thermal conductivity here, right. So, you need the temperature gradient also, right. So, this is the general formula that we have, assuming Newton's flow with Stokes assumption. So, you have this lambda and mu, the two lambda is the second coefficient of viscosity, right. So, you can see that you require these gradients, okay. So, you are calculating the flux at the phase, right. So, we have basically the value that we had at the center, we extrapolated and got the value at the phase, but then we also need to calculate this FB, right. So, FB requires the gradient at the interface, okay, because we are calculating there. So, for example, if you think of a very simple situation where you are talking about a incompressible flow, right. So, you can ignore this divergence term. So, this term will go to 0 and you can simplify it, okay, then you will get this basically mu del u. So, there is a gradient involved at the phase also, right. So, if you want to calculate this f perpendicular f a f and sum it everywhere. So, you will have f perpendicular f, which is coming because of the Euler flux, plus you will have this mu del u f dot n f. So, this is the phase gradient. So, you need both the phase gradient and the cell gradient. So, how do you basically get those gradients? So, what we will do, I mean, there are multiple ways to basically get those gradients. There are formulas like least square or the Green Gauss. So, we will discuss about these formulas in the coming classes. So, I will stop here. The one thing I want to keep you in mind is that you need basically gradients at the cell center as well as the phase center. Now, the question is how do we get it? The second question that we need to answer is that how do you basically ensure that upwinding is happening, okay. So, these are some of the questions that we need to answer, and then we are good to go, because we know the update formula, okay. We can calculate the flux using left and right value. If you know the left and right value, multiply with the area, you know the cell volume, we can use any scheme that you want here, you can use any flux scheme that you want, and we will be able to calculate. Okay. So, with that I will stop here and we will meet in the next class. Thank you.